meaningful connection to their land, and they have never ceded it. It's also important, I think, in the context of the recent referendum. And it's important at a medical conference where I think we're pretty good at doing stuff like this: blood, biomedicine, and so on. But I think most of us would acknowledge that Western medicine is pretty lousy at understanding how culture, country, body, mind and spirit fit together in a holistic, integrated understanding of social and emotional well-being. And if we actually listen to our Indigenous folks, we might learn something pretty important. This session is about the products, the rationale, and what's in the bag. We've got a great hour and a half ahead of us. Then I think we're going to do a group photo, with the expectation you're all going to be in your t-shirts, and there's going to be a moment of mass public nudity as we get from A to B. Yeah? Let's see how we go. I'm also under strict instructions from the grandfathers of THOR to remind you to be Australian, as they expect you to be, to question the generals, to not hold back. This is not meant to be a stuffy meeting. Call out the bullshit as you hear it and you see it. And only that way will we have a great, relevant meeting. So don't hold back in question time. I'm sure Denese will look forward to all of that. I'm going to introduce firstly Denese Marks. She's Associate Professor at the University of Sydney. She leads the product development team at the Australian Red Cross Lifeblood, and she's done that since 2008. She's had positions all over the world. She holds a bunch of research grants. She's very well published. She's a perfectly qualified person to talk about blood components, whole blood and leucocyte reduction. Denese.
So thank you, Russell. It's a huge topic that I have here, and I certainly cannot cover this in 15 minutes. So I'm going to tread very lightly, but I'm going to tell you a little bit about what's in the bag, but I'm going to leave a lot out. So there will be lots of opportunities for questions. Hopefully I don't give you any bullshit. I'll do my best. So what am I going to talk about? I'm going to focus on red cells and platelets. I'm just going to touch a little bit on plasma. I'm going to talk about a little bit about their activity and function in the context of bleeding, hopefully to set the scene a little bit for the great speakers that are going to come after I speak. I'm going to touch on leukoreduction, and I'm also going to do a quick comparison with low T to O negative whole blood. In Australia, we supply platelets, red cells, plasma, cryoprecipitate. We do not have freeze-dried plasma. We don't yet have frozen platelets. We don't yet have cold-stored platelets, and we don't have freeze-dried plasma. So let's look at red cell components and what's in the bag. The table here is taken from our blood components circular information, or the BCI, which is available on our Lifeblood website. And I've highlighted haemoglobin. And as Pat and Gear have already mentioned, when we give a red cell transfusion, we're giving haemoglobin. And there's about 45 to 50 grams of haemoglobin in a bag of red cells. And that is expected to raise the patient's haemoglobin by about 10 grams per litre, plus or minus, depending on the transfusion. So in Australia, red cells have a shelf life of 42 days, and they are stored in an additive solution called SAGM, which contains saline, glucose, adenine and mannitol. There's about 5 to 10 mils of plasma carryover in each red cell bag, and red cells are not irradiated unless requested. And I've just put a little reference there to our BCI. So if you want more information about blood components, because they are super exciting, please go to our website. So as soon as we take blood out of the body, process it, and effectively we manufacture it into blood components, the components change. And they change over storage, and we call this a storage lesion. And it happens to all blood components despite our best efforts to store them at the optimum temperature in optimum additive or preservative solutions. And the cells or the components in the bag change. So with red cells, their membrane changes as storage progresses. It becomes more rigid, and red cells lose deformability, which means they do lose their ability to wiggle their way through small capillaries. They also shed microparticles, and as a result of this loss of deformability and microparticle shedding, the red cell undergoes a shape change, loses its discoid donut shape, and becomes more spiculated and becomes what are known as echinocytes. Unfortunately, some red cells hemolyse during storage, and we also know that potassium does leak from red cells. As Pat alluded to, we need haemoglobin. Haemoglobin carries oxygen and delivers oxygen. But it's also important to remember that haemoglobin needs to release that oxygen to the tissues where it's needed for respiration. So when red cells are stored, there is less tissue oxygenation and less efficiency of oxygen release. And this also varies between donors. And I want to highlight some very, very recently published research from Cambridge University and the National Blood Transfusion Service in the UK, where they've looked at the ability of oxygen to the efficiency of oxygen release. And I don't know if there's a pointer, but what they showed is that as storage progresses, so moving to the right, the time for oxygen unloading or oxygen release increases. So the longer that red cells are stored typically, the longer it takes for the oxygen to be released from the red cells. And I think this is important in the context of trauma and bleeding. And the other thing to remember, and I think this is the really important thing, every blood component comes from a person, every donor is different. And so there is a large biological variation. One bag of red cells or platelets is not the same as the next one. And that's shown here very nicely in the differences in the way that the oxygen efficiency of oxygen release varies from donor to donor. And you might say, well, so what? If a transfusion is given for stable anemia, this is probably okay because 2,3-DPG recovers after 2 to 3 days after transfusion. But in the context of bleeding or a massive transfusion, this becomes a lot more important because there is less tissue oxygenation, and so the red cells that are being transfused need to compensate for that, and it could be suboptimal. The other thing I want to talk about very briefly are what we call biological response modifiers. So they could be cytokines, they could be proteins, they could be microparticles, mRNA, anything that's in a blood bag. And we might like to call those uninvited companions. And shown here is a table that from some work we did a few years ago looking at red cell washing. And what you can see is that there are complement and cytokines in every bag of red cell. Red cells are a reservoir of cytokines, and there's also plasma left over in every bag of red cells, even a small amount. So what? Well, what we did find is that even these small amounts, and these are in vitro experiments, can cause endothelial activation. Again, this is all part of the coagulopathy of trauma. So I think it's important to consider that red cells can cause endothelial activation, and we see this here shown. These lines here are from non-washed red cells compared to washed red cells. So there are things in the bag besides just red cells, and I think that's important to think about. There's also other things like non-transferrin bound iron that's released as red cells are stored, microparticles and pro-inflammatory cytokines. So many things in the bag besides red cells. So moving on to platelets, and again, I could talk a lot about platelets, but I'm not going to because my colleague, Dr. Lacey Johnson, is going to give you a very excellent overview of room temperature cold and frozen platelets, and she's going to go into a lot more detail. But what is important to know is that in every bag of platelets, there's about 250 to 300 times 10 to the 9 platelets, and that's a clinical dose of platelets, and very few leukocytes. Platelets in Australia are currently stored at 7 days at room temperature. We collect apheresis or pooled platelets, and they're stored in a mixture of plasma and a platelet additive solution, which is about 60 to 70% of the liquid that's in the bag, and that is an additive that we call PAS-E. And 100% of the platelets that we issue in Australia are irradiated, mostly because many of our platelets go to haematology, oncology platelets, patients which may be immunosuppressed. And again, for more information, please look at our circular of information. So platelets also undergo the platelet storage lesion, and lots of things can happen. They can lose their membrane glycoproteins, rearrangement of their membrane lipids, molecules can come from the inside to the outside of the platelet and make them more procoagulant. They can shed microparticles, they can release their granule contents, they lose their metabolic and mitochondrial activity. But very interestingly, their hemostatic function, at least in vitro, does not change. So just looking at these graphs, they are a little bit complicated, but I'll try to walk you through. So looking at the light grey bars, the first graph is clotting time of platelets that were tested using a TEG. And if we look from day 1 through to day 7, we see that there's very little change in the clotting time. If we look at the thrombin generation, what we see on day 1, platelets certainly generate thrombin, but what we see on day 5, shown here in these dashed lines, is that platelets that have been stored for 5 days actually generate more thrombin, and they do so actually a little bit faster. So storage, whilst it does cause a lot of changes in platelets, in their phenotype and their morphology and their biochemistry, they actually retain their hemostatic function in vitro throughout storage. As I said, I'm going very quickly, just giving you an overview. The other thing that I do want to touch on is leukoreduction, and we leukoreduce our components in Australia through centrifugation, separation and or filtration. And what I've shown you here is an example of what actually is there before and after leukoreduction, in this case with red cells. And we can see that there's about a 5 order of magnitude reduction in the number of white cells from pre to post leukoreduction. So why do we leukoreduce? Well, I hope you know the answer to that, and it's mostly to prevent transfusion-associated graft versus host disease, but also alloimmunisation, prevent CMV and a number of other things as well. What has been observed in trauma patients who received non-leukoreduced components, so before leukoreduction was introduced, that quite a high number of trauma patients develop microchimerism, where they have their own leukocytes, but they continue, adopt the leukocytes that are that come from the transfusion, and so they have 2 sets of leukocytes. Whether this is detrimental or not is still unknown, although some of these patients certainly have shown some symptoms of graft versus host disease. The good thing to know is that microchimerism occurs at a much lower frequency since leukoreduction was introduced, but it still does occur. So I guess the jury is still out on this one. It might be a topic for discussion about whether leukoreduction is a good thing or not. I'm just going to touch very briefly on plasma. I think everybody knows that plasma contains coagulation factors and it contains fibrinogen. It actually contains a lot of other things as well. We supply plasma frozen. It has a shelf life of 12 months frozen or 5 days once it's thawed. We also manufacture cryoprecipitate, and that is manufactured from plasma, and again that is used as a source of fibrinogen. At the moment we do not have freeze-dried plasma. So let's just switch tact a little bit now, and again I think I'm hoping to set the scene about components as part of balanced resuscitation versus other options. If you were to receive balanced resuscitation, that is platelets, plasma and red cells at 1 to 1 to 1, if you were in a hospital in Australia, you would get 720 mils of fluid. That contains about 230 mils of additive solution, which contains salt, sugars and liquid, water, saline, and 70 mils of anticoagulant. So that's actually 300 mils of liquid that is not blood, and 420 mils of blood, giving you a total of 720 mils. Or alternatively, if whole blood was available, and I emphasise that it currently is not, then you would receive platelets, plasma and red cells all in one bag, and that would be a volume of 465 mils. So I guess it's probably a good thing to say, well, what is in the bag if you were to receive whole blood compared to components? And this is from some work that was done by Dr. Joanne Tan in my lab a few years ago. And, whoops, sorry, how do we go back? Is there a back button? A red one? Yep, there we go. So if we look at haemoglobin, in whole blood, there's actually more haemoglobin than a red cell component, and that's because the blood, when whole blood is manufactured, is not centrifuged and separated, so red cells are not lost. It still can be filtered to remove leukocytes, but there's actually more haemoglobin in a bag of whole blood compared to red cells. If you look down the bottom, you'll see that there's about a quarter the number of platelets, and that's because a standard pooled platelet comes from 4 bags of whole blood originally. So if you times that by 4, you get the same number, and that's the difference. And obviously there's not many residual leukocytes in any of these products. So I guess another thing to think about is that whole blood is being stored outside the body just as blood components are, so it does undergo a storage lesion. And what is shown here is the platelet count as whole blood is stored for 42 days. What you can see is that it does decrease quite dramatically, which looks rather scary. But something magical happens when you store whole blood in the fridge, and that is the platelets are cold stored. So when you cold stored platelets, they change, they become more activated, and actually whilst we're seeing a huge drop in the platelet count, we see a very large increase in thrombin generation if the platelets are stimulated. And similarly, that's the amount of thrombin, the lag time to thrombin generation decreases, so the platelets can be activated more once they have been stored in the fridge, which I think is quite an interesting thing to think about. So lastly, if you want more information, please ask me, or please go to our website if you have never visited that before, and there is lots of lovely information for health professionals about blood components. Thank you.
Perfectly on time. Thank you, Denise. Our next speaker is Andrew Beckett, who's a Lieutenant Colonel in the Canadian Armed Forces, where he serves as a trauma surgeon and critical care physician and currently Chief of General Surgery. He's served in Yugoslavia, Afghanistan, Africa, Iraq, a bunch of places. He has a long-standing interest in military history since the age of 6. He's currently president of the Trauma Association of Canada. Many people in the room, very much great friends of the TAC through the Australian Trauma Committee too. And he is medical director of the trauma program at St Mike's in Toronto. He's going to talk to us about fresh frozen plasma versus freeze-dried plasma. Thanks, Edward.
Thank you. Well, I'll just, while they're sorting out my talk there, I will just make a couple comments. Anyways, it's a great pleasure to be back here among friends of THOR and folks in Australia, which, unfortunately we haven't had many connections with since the pandemic. But what I'm going to be talking about today is the comparison between dried plasma and frozen plasma. And we'll see if we can get that up. Yeah, okay, I'll just grab my laptop.